Welcome to this explainer. Let's get right into it, because today we are embarking on a seriously fascinating journey. We're going to unpack the absolute magic behind modern artificial intelligence. You know, if you've ever found yourself wondering how tools like ChatGPT, facial recognition, or even self-driving cars actually work under the hood, you are exactly in the right place. We're not just going to skim the surface here. We're actually going to build an artificial neural network from the ground up, discovering exactly how machines learn to perceive our incredibly complex world.
I want to kick things off with this quote because, honestly, it perfectly frames our entire explainer. Think about it. For decades, computer science was entirely about giving machines very strict manual instructions. It was basically a giant calculator. But the real game changer happened when researchers looked at the 86 billion interconnected neurons in the human nervous system and asked a wildly brilliant question. Could we mathematically imitate that biological learning process?
All right, so here is our roadmap for today. We'll be hitting 1. Beyond human limits. 2. Anatomy of a neural network. 3. The spark of nonlinearity. 4. Learning from mistakes. And finally, 5. Mastering the real world. Let's jump in.
Section 1. Beyond Human Limits, Feature Engineering.
To truly appreciate the concept of an artificial brain, we first have to understand the massive roadblock early artificial intelligence ran into. For years, traditional machine learning relied on a process called feature engineering. Basically, humans had to manually tell the computer exactly what variables to care about. Say you're trying to predict wildfire severity, human experts had to manually handpick data points, things like temperature, relative humidity, and wind speed. It's kind of like giving two photographers the exact same camera. The first is an absolute master who knows exactly where to stand, how to set the exposure, and they get a perfect shot. The second is a total novice and gets a terrible, blurry shot. In traditional machine learning, the algorithm is entirely at the mercy of the human expert providing those features. But what if there's a crucial hidden pattern that the human just missed? Well, the algorithm could never learn it. For really complex tasks, like recognizing a sleeping cat in a photograph or translating the nuances of human speech, handcrafting every single rule became literally impossible. We hit a wall. Deep learning changed everything by allowing the computer to automatically discover these patterns on its own.
Section 2. Anatomy of a Network, the Artificial Neuron. So how do we actually build a system capable of discovering patterns entirely on its own? It starts right here with the 5 mathematical steps inside every single artificial neuron. First, it takes in inputs. Let's stick with the temperature and humidity of our wildfire example. Now, not all inputs are equally important, right? So it multiplies each one by a learned weight. It then adds all these up, along with a baseline threshold called a bias. Finally, it passes that weighted sum through an activation function, and boom, it fires off an output. That's the whole shebang, just a simple sequence of math. But while one neuron isn't particularly smart on its own, the real magic kicks in when they team up.
By stacking these simple neurons into networks, we get something incredible. The flow of information happens across 3 main layers. The input layer simply receives the raw data, like the raw pixels of an image. But the heavy lifting? That happens in the hidden layers. Think of these like a highly specialized factory assembly line. The first hidden layer might just look for super simple edges or lines. The next layer combines those into curves, and a deeper layer combines those into a recognizable human face. Finally, the output layer gives us the prediction. When we stack many of these hidden layers to divide and conquer these wildly complex tasks, we create what is famously known as deep learning.
Section 3. The spark of nonlinearity, activation functions.
But wait a second. If we just stack a bunch of simple math operations on top of each other, we end up with one giant, totally useless linear equation. And this is where the activation function comes in. This is absolutely crucial. It's the mathematical step that transforms a neuron's basic weighted sum into a nonlinear output. Without this spark, our deep learning factory would just produce a flat, rigid line. But look around. The real world isn't a straight line. Things like wildfire smoke dispersion in the atmosphere or the fluctuations of human speech, they are curved, messy, and deeply complex. Activation functions give our artificial brain the flexibility it needs to actually map out those complex realities.
Let's look at how these specific activation functions evolved, because they solve some massive roadblocks in AI. Early on, researchers used the sigmoid function. It smoothly compresses outputs between 0 and 1, much like a probability, which is great for the final output. But in deep, hidden layers, it caused a massive issue called the vanishing gradient problem. Imagine a relay race where every runner accidentally drops half of the baton before passing it to the next person. By the end of the race, there's literally no baton left. That's exactly what sigmoid did to the learning signal in deep networks. The signal just vanished.
The absolute breakthrough here was ReLU, the rectified linear unit. It is incredibly simple. If the input is negative, just output 0. If it's positive, pass it through completely unchanged. This simple trick saved the relay race, keeping the learning signal strong and fast across hundreds of layers. And then, when we finally need to pick one class out of many, say deciding if an image is a cat, a dog, or a horse, we use softmax at the very end to give us nice, clean, structured probabilities.
Section 4. Learning from mistakes. How networks learn. Okay, so we have our architecture and our nonlinear spark, but how does this artificial brain actually get smarter over time? Think about it for a second. When we first build this network, all those weights that determine the importance of the inputs, they are totally random. It knows absolutely nothing. So how do random starting weights eventually transform into highly accurate real-world predictions? It all happens through a continuous, relentless loop of trial and error. First, the network makes a raw prediction. Next, it measures exactly how wrong it was using something called a loss function. Imagine throwing darts at a dartboard. If you hit the wall, your loss is huge. If you hit the bullseye, your loss is 0. The network takes that exact error and sends it backwards through the entire system in a famous process called backpropagation. It figures out precisely which weights caused the mistake, and finally, it updates those weights so it does just a little bit better on the next throw. The mathematical engine driving this entire update process is called gradient descent. Imagine you're a hiker trying to reach the bottom of a deep mountain valley, but you are caught in incredibly heavy fog. You literally can't see the bottom. So what do? You feel the ground with your foot, you find the steepest downward slope, and you take a small step in that direction. You repeat this over and over until you reach the valley floor. That is exactly what gradient descent does mathematically. It takes step after step down the slope of the error curve until it finds the absolute lowest possible loss.
Now, learning isn't just about making corrections down the mountain, it's also about organizing the data efficiently so our network doesn't just get completely overwhelmed. We don't feed all our data in at once. Instead, we break it into smaller groups called batches. When the network has finally seen all the batches one time through, it has completed one epoch. We also have to control our hiker's step size with the learning rate. If the step is too big, the hiker leaps right over the valley. If it's too small, it takes years to reach the bottom. And instead of just using basic gradient descent, we use advanced optimizers like Atom. Think of Atom like a smart GPS, adapting the learning rate on the fly to help our model navigate that complex landscape smoothly and quickly.
Section 5. Mastering the real world. Generalization. So, we've built our network and we've trained it, but we have one final critical hurdle. We have to ensure our artificial brain is actually mastering the real world. The entire goal of deep learning is to generalize to new, unseen data. If our model is too simple, it underfits. It just hasn't learned enough to be useful. But the much more dangerous problem is overfitting. For example, in the real world, models are deployed to detect and block abhorrent, illegal material like CSAM. But if a model overfits, kind of like a student who only memorizes last year's exam questions, it might perfectly flag the exact training data, but it will completely fail to recognize new, unseen variations of those threats in reality. It's memorizing the noise rather than learning the underlying concepts. And an overfitted neural network completely falls apart the second it hits the real world.
So, the crucial point is how we actually stop this from happening. Well, we use a separate validation set of data as a sort of pop quiz to check if the network is actually learning real concepts. If the validation score stops improving, we use early stopping to just halt the training before it starts memorizing. We also use an incredible technique called dropout. During training, we literally randomly turn off a percentage of the neurons. Why on earth would we do that? Well, think of a group project. If one student does all the work, the others learn absolutely nothing. By randomly dropping neurons, we force the entire network to share the workload, meaning the model develops a much more robust, generalized understanding of the data. We also use L2 regularization to keep our mathematical weights small, and data augmentation to show the model slightly modified images. Together, these tools ensure our artificial brain is truly ready for reality.
And there you have it. We have taken biological inspiration, transformed it into interconnected mathematical equations, given it the spark of nonlinearity, and taught it to optimize its own mistakes perfectly. We went from manual, tedious human limits to machines that can literally teach themselves the hidden rules of the universe. The principles you've learned today are the exact same ones powering the largest, most advanced AI models in the world. So as we wrap up this explainer, I want to leave you with one final thought. Equipped with this knowledge, what incredible hidden patterns is an artificial brain just waiting to discover in your own data? Thank you so much for joining me. Keep learning, and I'll see you in the next explainer.